Have you ever wondered how real-time transcription services like Fathom AI work? Today, I'll walk you through designing a scalable real-time transcription service. Let's first get the key requirements clarified. A real-time transcription system needs to support a global audience, ensuring accessibility across different regions. It must process and transcribe speech with minimal delay, even under high traffic conditions. But what happens if a participant loses connection? To maintain a smooth user experience, if a participant loses connection, it shouldn't waste resources retransmitting everything. Instead, it should prioritize the latest transcriptions so they can seamlessly rejoin the conversation. And finally, the system must ensure post-meeting accessibility, allowing users to retrieve transcripts and insights even after the meeting ends. With our key requirements in mind, let's look at how the system is designed to meet them. It all begins with the client, where users participate in a meeting. The client sends audio data over a WebSocket connection to the load balancer, which ensures incoming traffic is evenly distributed across our WebSocket servers. These servers manage live streams of audio chunks from participants. The audio chunks are sent to the audio processor, where pre-processing tasks like noise suppression and audio normalization are performed. Once processed, the data is pushed to the message broker, a key component that handles asynchronous communication between services. The transcription generator then takes these audio chunks from the broker, streams them to a speech-to-text API, and generates the transcriptions. These are published back into a second message broker to ensure the data flow remains decoupled. Meanwhile, we use a subscriber component to collect the transcribed chunks and store them in chunks transcription storage that ensures consistent transcription delivery to clients. Beyond real-time transcription, the system also supports post-meeting processing. Audio and transcription data are saved to persistent object storage. The post-meeting handler listens to the events on meetings being ended and triggers additional workflows, like retrieving persisted meetings data and integrating with a large language model for advanced use cases, like post-meeting summaries or key highlights generation. Finally, processed data is stored in the database, where a change data capture mechanism syncs updates to the users who have set up notifications for specific meetings. And a post-meeting service can be set up for enabling features like user-accessible archives or insights dashboards. As audio data flows through the system, scalability and reliability are key to handling a large number of concurrent meetings. Let's walk through how we've designed this pipeline to meet those demands. First, the load balancer plays a crucial role in handling client reconnections seamlessly. If a WebSocket server goes down, the load balancer directs clients to reconnect at slightly jittered intervals, preventing a surge of simultaneous reconnections that could overwhelm the system. Additionally, it enforces an exponential back-off retry strategy, ensuring that repeated failures do not cause unnecessary strain while maximizing the chances of a successful reconnection. Also, the WebSocket server must be stateful. It holds critical mappings, such as connection IDs to meeting IDs, speaker usernames for each connection, and the latest received chunk ID for each connection. This state ensures delightful customer experience, smooth failure recovery, and session continuity. Next, each audio chunk is assigned a unique sequence ID. This ID is essential for stitching the chunks back together in the correct order during transcription and further processing. To ensure system reliability, the message brokers must guarantee data persistence. This allows downstream components to reprocess any missed chunks in the event of a component crash or temporary outage. For cross-region scalability, An event bus such as Google PubSub can be used for the second broker. This allows subscribers from multiple data centers or availability zones to listen to the same event bus for any specific meeting, ensuring a highly available system. Monitoring also plays a critical role. The system must watch for unstable internet connections, dynamically adjusting streaming quality to provide a seamless user experience. It should also detect missing chunks across the pipeline at scale, enabling proactive mitigation of potential issues. Finally, for handling the flow of data from transcription storage back to the WebSocket service, a hybrid push-pull mechanism can be implemented. Push ensures the system handles spikes in traffic efficiently, while pull provides a safety net with retry logic to recover missing chunks for any specific meeting. Engineering teams can start with one mechanism and iterate to implement both, ensuring an optimal balance between throughput and reliability. This robust design ensures a scalable and fault-tolerant system. But how can AI elevate the real-time user experience by generating actionable insights? The WebSocket servers stitch transcription chunks into a continuous stream, preparing the data for lightweight inference models. These models operate in real time, flagging critical moments, summarizing discussions, and identifying actionable insights, such as assigning tasks or recognizing decisions. Now, there's an important design decision here. Should the AI inference model be deployed directly on the WebSocket server where the transcription chunks are processed? Or should the stitching and AI runtime models be deployed as separate, standalone services? Each approach comes with its trade-offs. On one hand, running AI inference directly on the WebSocket server minimizes latency, offering a fast and seamless experience for users. But it can lead to resource bottlenecks, especially if the AI models require significant computational power. On the other hand, using standalone stitching and AI services allows for better scalability and flexibility. These components can be independently updated or scaled, ensuring reliability even under heavy loads. However, this approach increases system complexity, making it harder for the engineering team to maintain a clear understanding of the entire architecture. For an early-stage product or MVP, it's often practical to stack all components, including stitching and AI inference, directly on the WebSocket server to simplify the architecture and reduce development overhead. As the product scales and usage grows, these components can be separated into standalone services to improve performance, scalability, and maintainability, ensuring the system can handle increased load without compromising efficiency. By combining these design considerations with cutting-edge AI, the system transforms raw meeting data into meaningful outcomes, ensuring that every discussion is actionable, impactful, and easy to revisit. Let's recap what we've built and the key takeaways for designing a scalable real-time transcription system. At its core, the system is designed to handle high-concurrency audio streams, ensuring participants receive real-time transcriptions with minimal delay. To achieve this, we leverage a stateful WebSocket server to manage essential mappings and support smooth failure recovery. The load balancer plays a crucial role in maintaining stability, efficiently distributing connections across WebSocket servers and handling reconnections. In the event of a server failure, it directs clients to reconnect at slightly jittered intervals and enforces an exponential back-off retry strategy to prevent system overload. The pipeline is structured for reliability and scalability, with unique sequence IDs for audio chunks to enable seamless stitching and ordered processing. Message brokers ensure consistent data flow, while an event bus like Google PubSub guarantees availability across regions. Robust monitoring detects connectivity issues, adjusts quality dynamically, and identifies missing chunks to maintain a smooth user experience. To handle surges in traffic while maintaining reliability, a hybrid push-pull mechanism between transcription storage and the WebSocket server balances throughput with safe retry logic for recovering lost chunks. With this foundation, we extended the system with real-time AI-driven features like tagging key moments, generating live summaries, and extracting actionable insights. These runtime capabilities are supported by lightweight AI models deployed thoughtfully to balance performance and scalability. Thank you for watching. If you enjoyed this breakdown, hit the subscribe button for more insights into building scalable tech systems. Let me know in the comments what you'd like me to tackle next.